WhatsApp for you to in our WhatsApp group for you to slide your attendance. Okay. Without further ado, I would like to share my screen and we go straight to our lecture. Yeah. All right. This is my lecture. Thank you very much for attending all. I would like to record this first. So, okay. All right. Okay. Today we're going to start with second lecture. This is about analog and digital devices and also transfer functions and also data analysis. Yeah. So it's going to be a very short lecture, probably about half an hour. Then we're going to continue. The next lecture is on Tuesday. Okay. So let me do the slideshow on the current slide. So it's about analog and digital transfer function and data analysis. We go one by one. Yeah. So when we look at analog and digital um, devices, an instrumentation component can be in analog and digital. The difference between digital and analog, it means that in analog we have a continuous data, yeah, not a discrete, so it's continuous. Whereas the digital, it's discrete, yeah, and it can be something like this. The same graph in digital, it might be something like this, yeah. Let me show you. So this is the digital graph and the analog graph. So it's discrete. Only one here is, if you can see in digital, you have one value and next value and next value, whereas in the analog is smooth curve. So there is a difference between the analog and digital uh, uh, devices. Analog is continuous and digital is more or less discrete in time. So because of that, we find that in digital, yeah, it will have some error. Yeah, digitization first, what we call digitalization of the data, whereas the data is being digitized. It means that what's in between, some numbers between the data is gone, yeah, and also discretization of times. So it means that you have only one data at one particular times and then another time, but not in between. So there's two errors in digital device, yeah. But anyhow, this day, because of the digital has using a very large data, sort of a big number, the number of bits being used is very large. So more or less, that error has been reduced. Yeah. Digital data representation may be in analog or digital. In analog data, there is a smooth and continuous variation. And in digital data, number are represented in terms of binary bits 1 and 0. Yeah? So we need to know about what is the transfer function. engineers usually represent the instrumentation system in a block diagram, something like this. Yeah, it's easier. Yeah, to draw an actual diagram, actual circuit for signal conditioning or actual transducer is very difficult. So we represent it with uh, uh, block diagram like this, and we use transfer function to establish the relationship between the output and the input. Yeah, if you put input, what is the input, what is the output come out. Yeah, so the transfer function in short is just a relationship between input and output. Yeah, and for that, we transform this block diagram into another block diagram, which actually contain what we call the transfer function. Yeah, and with this function, we can estimate what is the output from, say, the transducer here. Yeah, if the temperature here is 20 degrees, what is the temperature at the output? What is the output of the transducer? Probably 2 volt, 3 volt, whatever. Depends on the transfer function and also in the signal conditioning and the output voltage. Yeah? And here, you can simplify probably two transfer function become one in a simple block diagram. Yeah? The job of engineer really first thing in design to find this transfer function. If you got this transfer function, then your design will be smooth and you can do the analysis. Yeah. The relationship between the output and the input is given by, in this example, V equal to 0.00 temperature. So this is another sort of simple relationship. It can be of any others. Example here, yeah, suppose we have example here, example 2.1. Suppose the temperature range. So we have something like this. Say this, suppose this is our transducer, yeah, and also the signal conditioner, something like this, and we are subjecting our transducer and the signal conditioner inside this from 20 degrees to 120 degrees. It's linearly converted to a standard range of 4 to 20 milliamp. So we put 20 degrees, it gives us 4 milliamp. If we put 120, it gives us 20 milliamp. So you can draw a line, a graph from this data, the first data, and what current will result if the temperature is 66 degrees. Yeah, and what temperature just 6.5 milliamp represent if we measure at the output is 6.5 milliamp. What is the temperature? So the solution is first determine the input and the output relationship first. What is the linear equation relating the temperature and current? So if we look at this, yeah, we have this our block diagram. Inside this, we want to know what is actually the transfer function or the equations that relate output to the input, the output to the input. So from the graph, at 4 milliamp, we are 20 degrees. See, at 120, we have 20 milliamp. So these are the equations that represent the transfer function inside this block diagram, and we call it from this graph, we can say that, okay, I equal to m times t plus I naught. I naught is the current that is when the line intersect the current axis. Yeah. So okay. And then put all the value into the linear equations. Then we have this equation. 4m equal to that. 2m equal to 20m equal to this, where the temperature for in the 4m is 20 degrees. Temperature at 20 milliamp is 120 degrees, and we have I naught. Yeah, and if we subtract equation 2 with equation 1, and this will give us something like this. So we have the slope of the equation that is m is equal to 0.16 milliamp per degrees, and then we can find I naught by inserting or substitute m in either equation 1 or equation 2. Then we find that I naught equal to 0.8 milliamp. So the transfer function now is given by this equation. So from here, we can answer the question 1. What is the current for T equal to 66? So if we put 66 here, then we can find the current. Yeah. And if we inverse or rearrange this equation and uh, find the temperature for I equal to 6.5 milliamp, then we have something like this. Yeah. In our engineering, okay, when we do the calibration, we do the calibration, normally we calibrate equipment by inputting the temperature at the input. Yeah. So and we got this equation, and then when we use the equipment, normally we inverse this. This when we use the equipment. Normally when we use the equipment, we do not know the temperature. We use our thermometer and put it in the environment where the temperature that we want to measure. So what we get is the output from the transducer. That is the current, say current here. So we would like to know what is the temperature. So this equation. Question 2 is, and the scenario is when we are using the equipment to obtain the temperature, and this the question 1 is actually when we do the calibration. Yeah. So sometimes the graph, the linear graph of the transfer function, also we call it calibration function. Yeah. Data signal transmission. Normally, when we have instrumentation, we do not stay there. We would like to transfer our data from one place to another place. I have experience where I used to make one instrumentation to transfer data for about 100 meters. Yeah. So how we do that? We use current flow. And why 100 meters? Because normally our environment that we want to control is far away from our control room. So everything needs to go to the control room, and our sensor is in the field, measuring the temperature or measuring the pressure, measuring the movement, measuring the force, and all this data need to transfer. Yeah? For electrical instrumentation system, we use a range of electric current carried in wire as a data signal transmission. Yeah? And the range is 4 to 20 milliamp. Yeah? We use current. We do not use voltage. It's hard to use voltage. If we use voltage, we find that end of the wire, when it's reached to the control room, we subjected to the environment or the change of the resistance in the wire that is transferring the data. Yeah? So if we are measuring the voltage, then I have experienced also this when we put it a wire across a field, then at 20, so at in the morning, like now, yeah, then the ground temperature is about 27 26, yeah, then the wire got the wire resistance is very small. So whatever the transducer uh, put at the input at the end of the wire, the voltage, and at control room we got that almost that voltage. But when it comes to at say 12 o'clock in the at noon, and then we find that the voltage become reduced. Why? Because the cable resistance has some effect, has suffered some heat expansion. So the resistance in the cable is increased, and because of that, if the voltage being sort of uh, sorry uh, input by the transducer at the end of the wire is say 1 volt, then because of the resistance, the end at the end of the of the cable in the control room probably say is only 0.5 volt because of the resistance inside the wire is changed. When it change the output of the voltage at the end, so it give error. So the best way is to use the current. So regardless what is the change of the voltage, change of the resistor resistance in the current, yeah, and in the cable, the current stays, yeah, conservation of charge. So if the transducer produces 4 volt 4 milliamp input 4 milliamp into the cable, then at the end also we receive 4 milliamp. So there's no loss of data. Of course, there's a consequence. That means that the voltage could be higher at the end. But we don't care about the voltage. We care on the currents. And also some of the data signal transmission, we do it using a pneumatic instrumentation system. We use the range of gas pressure carried in the pipe, yeah, something like this. Yeah? Why use current? Current is used instead of voltage because the system is less dependent on load. Yeah? Voltage is not used for transmission because it's susceptible to changes of resistance on the line. Look at the example below. So if you look at the example below, we have a sensor here and we have cable. It remind you in a real world, yeah, when you are doing the instrumentation, sometimes the sensor here is the plant and the control room is about 100 meters, sometimes up to 1 kilometer. It's happened. Yeah. I have a job with if I'm not it's with Petronas, yeah, subcon to us to do some sensing, to sort of install some sensor on the pipeline, yeah, crude oil pipeline, and the control room and the pipeline is about a kilometer. The sensor where the pipeline where the sensor is being installed and the control room is about 1 kilometer. Imagine how far, how long is so imagine how much resistor can change in between this due to temperature. So sensor here, look at example below. Sensor to carry to current converter. Yeah, sensor to current converter is designed to launch a current into wire regardless of load. So whatever the load doesn't matter. Here also some current, some sort of resistance here. If there is problem with the wire or transmission line, current still held in constant, although a new wire is added. So suppose there is a cut here, we put a new wire, we have some resistance there, but the current from here to here is still the same. Yeah. So when you in the control room, you can have a standard load that is in a sort of a control environment where the load does not change. Then we can get the voltage after that using the current multiplied with the load. And here the load here does not change. Yeah. if it's in the control room. But here it can change. Yeah? So, but the current here does not change. Yeah? So we have a data fidelity, what we call it. Significant figure. This is another thing. I think this is just repeat of what you have learned in your first year. Significant figure are digits, places actually read or known from the measurement of operation. Example, a digital multimeter measure the current through 12.5 kilo ohms resistor as 2.21 milliamp using a 10 milliamp scale. Find the current and the voltage across the resistor. And so if this the resistor, this the current, so we know that if we multiply this, then we have the number. Yeah? But not all this number is significant. We know that the current is three significant figures. The current is three significant. Thus, the voltage should be also three significant figures. 2.5 is too much. Yeah, it's no longer significant. We look at the current here, where it's three significant figure. Then this what. So we should represent the significant figure based on our sort of reading. Yeah. So why we didn't use the resistance? Because resistance is a constant. Yeah, something that we don't measure. We measure the current. So this the where the errors going to involve. So anything more than three significant figure is already in error. So we use that, yeah, as a guideline. So in the statistical data, yeah, consider the case of you are asked to measure temperature in 8 locations in a room, and the value you have obtained were these or these 21.2 degrees C, 25.0 degrees C, 18.5 degrees C, 22.1 degrees C, and so forth. What is the value that can describe overall temperature in the room? Is it 21.2 degrees, 18.5, or 19? The answer, well, depends here what you want. Yeah, statistical analysis can help to analyze the data. In this case, we use mean. Probably we have a room and we want to use it as something that is on average. So we use mean. Okay, but I have an experience also when we do temperature profile of a aircraft cockpit. Yeah, we have a cockpit where the pilot sit. Yeah, and we want to get a temperature profile. At that point, we use really point by point. We do not use a mean. Why? Because we are studying the pilot comfort. Yeah? When the pilot sort of flying an aircraft, yeah. So especially the fighter, yeah, they do not have some a luxury of aircon, something like sort of transport aircraft. In a fighter aircraft, normally they taking the outside air to cool the pilot. Yeah. So we do the profile, and sometimes we really need the actual temperature at certain spot, especially when it's at the face. We find that the pilot actually is very critical to get the temperature around the face cool enough to make the pilot feel refreshed. I think you also experience this. Yeah, when you are driving, sometimes you are driving, you feel very tired, sleepy, and then suddenly you blast your aircon to your face, suddenly you feel fresh, even though the rest of the body is still hot. So it depends on what you want to do. In this case, we use the analysis of mean to find the sort of represent the overall or the average value of the room. But depends on what you are doing. But the statistical data analysis is very important to us to give some meaningful solution. Yeah. So we have this arithmetic mean is sum of all the data that we have and divide how many data we have. Yeah. So we have also standard deviations, which I'm not going to go. I will go in detail, but I think you have have covered this in a lot of other subjects. So we're going to go very fast here. So example here, given two data, and even if we deal with this, then you have also the mean something like that. Sometimes these are these things, the mean does not actually represent uh, everything. Yeah. Uh, the deviation also need to be used to get how well distributed is the data is. So there's a normally in statistical data we need to know more to know both the deviation or standard deviation and also the uh, mean. Yeah. So these are the example, yeah, example. So you can go through this. I think you can get it from the e-learning. And so this is how we do by tables, yeah, the value, and this the mean and deviation, and then or standard deviation, or this, yeah. So with that, I think we are reaching our sort of end of our uh, lecture for today. Yeah. So we're going to continue more on this on Tuesday. Yeah. Today is just a brief, very small, very short lecture. So with that, I say thank you very much for you all to join us. Yeah, for join this class. If you have any question or anything you want to ask, go through the either you ask me through the WhatsApp, or you can email me your question. Also, I will try to answer every answer every question that you ask. So with that, thank you very much for attending this class. Yeah. All right. So I will end this meeting. Yeah. For everybody. Thank you very much. Assalamualaikum.